before, but
Sure, you share your screen too.
uh
At the bottom.
Oh, yeah.
oh, okay.
Oh,
Oh, there we go. It's working. Okay, so basically, something that I find really, really fascinating and interesting to me is fluid simulation. So that's what we're going to be talking about today. Um, and something specifically called particle clustering. Um, so what is it? It's a way that you can simulate fluids in ShaderToy. It's maybe not the most efficient way of simulating fluids, but it's very fascinating. And the way that you solve it can be maybe helpful for some kind of situation or scenario. It works particularly well with 2D simulations, in my opinion. But this is a one that I programmed in 3D that got working pretty well. So it's particle based. So most simulations on ShaderToy are Eulerian based, and that basically means that they work per cell rather than per particle. So like if you think about a grid like this, instead of simulating like these tiny points, it's just like an entire block, which that's great for like for example simulating air or smoke. But the second you want to have anything with any kind of surface or topology like water, it just kind of fails. I've tried in the past to get it some kind of Eulerian simulation to work, but it's just you need an extremely high amount of cells or pixels to do anything remotely that looks like water. So as far as I know, the first person who worked on this or did something similar who created particle clustering was Michael on ShaderToy. So shout out to him. There's also not really any papers written on this. So as far as I know, because it's not necessarily it's pretty new. I think Michael did it like just a few years ago on ShaderToy, so like not much stuff is known about it. So that's cool, I guess. I guess before I continue, does anybody have any questions about anything that I haven't clarified yet?
I mean, so like,
Yeah.
I'm assuming you're getting into how it works, but like, how is it different from using like, a unit system?
Yeah. So the weird thing about it is it literally is a grid system.
Yeah, right.
So because you have the particles, the idea is that for every single cell, you store 2 particles.
Okay.
And so why it's called particle clustering is because if you have 3, you need to condense it back down to 2.
Right.
So you combine them together and then you have 2. And then one just has some extra mass. And then later on you scatter it if you have extra space. So, yep. So the reason why you kind of have to use particle clustering in ShaderToy is because there is literally no vertex shader. And what that means is, you know, all of those meshes and things that you have with regular graphics, you can't even render a mesh. So it's literally just per pixel processing. You can't write to any other pixels than the current one you're processing, which can be weird at first when you think about it, but it's actually super efficient if you do it properly. Let's see. Oh yeah, it also works with like super old graphics APIs. Like if you can have a fragment shader, it will run particle clustering. And basically what that means is like 10-year-old graphics hardware just chug us through this pretty easily. So clustering works backwards instead of forwards. So usually you have a particle and you move it and then distribute it to the grid. So, but I guess I should probably answer what first about the grid is why do we need a grid in the first place? Why can't we just have a bunch of points? So the points themselves can't really communicate with each other. If you had a point right here, there's no correlation between this one and this one up here. The only way that you'd be able to really do that is by using some kind of like insane tree structure, like I don't know, like a BVH or something, or a KD tree. And at that point, like it's so weird and inefficient that you just really can't do that many particles. So the idea is if you have a bunch of points and then you draw them to a screen, they will be like a blurry representation of all the kinds of data. So like density and velocity are the two most important ones. And from the pixels on the screen, if you look around at the other pixels, you can actually see the literal gradient of the pressure and the velocity. And so that's how you can get like the Lagrangian formula and stuff that looks really scary with like differential equations and everything. Because you have the gradient right here, it just automatically solves it. Because you have all that information. You don't need to generate it using weird calculus. It is literally just like finite differences. That is literally it. Let's see. So, any questions so far? Nope. Great. Yeah, so the first thing we do is we have to consider what happened last frame, which is all the information is already on the grid. So because the information is already all on the grid, we have to gather them to each point. So this is where it gets a little bit tricky to do just on the board, but the way that you gather something to a point, because the grid information is stored at the center of each of the cells. And has anybody heard of like linear interpolation? Yeah. Okay. Have you? Kind of. So it's a super standard method of basically blurring an image. So let's say you have like this point here. Well, you take weights at each of the corners, and based on the distance to all four corners, each one will be added together. So like if I'm closer to this one, it's going to be weighted higher over here. I wish I had an image because it would make a lot more sense. But yeah, so just imagine you're just looking at a blurry image, and that's what this function does. So once we grab all of the density and velocity, we can move every single particle on the grid. And this is where it starts getting really weird, because we're at this current red cell right here. But this cell could technically have a particle that goes and jumps into this cell. So we'd have to simulate this one also, alongside the one that we're currently on. So all of these particles also need to be moved and simulated. But wait, this one also, and this one also. So you actually have, 9 cells that you're calculating, and if it doesn't end up in the cell, it literally just gets thrown away. for the most part. Some of the information is just the general picture of it is a bit valuable. But yeah, so it sounds really inefficient, right? Um, but this is where the idea of memory comes into play. Each one of because all of this is really close together in memory, you can just hit cache lines super, super fast. And then finally, once you do that, you collect all the particles, and then you're all good to go. As well as distribute all of the particles mass to the actual grid node in the center. Any questions there? I know that's kind of a lot to take in.
What specifically are you doing to calculate the physics? Is it just
Yeah,
is it random movement, or what's the?
so
I understand, like, once you get the going, then it makes sense, then it's easy to be like, oh, this goes here and here and here. Like, what starts the
yeah,
movement?
so what I've described right now is just there's no pressure.
Yeah, right.
Yeah, so literally just particles floating around in space, conserving their velocities. So I'm glad you brought that up because this is the most hardest thing to solve in any part of the simulation. So going back to like that density, if we have a point here and we know it's a density, oh, this is a terrible marker. Once it's affected, right? Let's say this density is like 1.2, just some arbitrary value. And we want to keep the density at like, 1.0. So the way that this particle will push all other particles around it is by putting velocity data back into the grid.
Okay.
So because we're only on this cell, right?
Yeah.
All of these are just imaginary. So technically, it will push this velocity
Right. And
this
that's,
way.
so like each particle is velocity mapped to the grid's like determined velocity based on
Yes.
pressure, not pressure, but
Yeah.
density, I guess. Yeah.
So every single one will contribute to this center cell,
Okay.
and they'll all try to push. And so instead of it being like, one whole unit that way, it'll probably be like, I don't know, something really tiny like this, because it's pretty uniformly distributed.
Right.
Because it averages them all. Yep. Any other questions there? No? Okay. Perfect. Yeah, so what this method is called, in reality, the one that I'm using right here is like an idea of a mix of MPM or PIC. If you're ever interested, those are really good papers to read. They can be a little bit hard to understand, but like just hit me up if you have any questions. But yeah, just the idea of distributing everything to a grid and then pushing it all back to the particles again. That is the general idea of PIC or MPM. And if this is confusing, like this is really new technology. I think NPM was literally just released like, I don't know, maybe like 15 or 20 years ago. And this is like stuff that like Disney and like Pixar use. I think Flip might be a little bit more popular, but it's just the paper right after PIC. So it's like, it is really, really new. Really, really cutting edge technology. Yep. And now we have like a link to the code base. So you can actually see what this looks like through code. Maybe I can put this on the SIGGRAPH chat. Everybody has their computers. Okay. So this is the part where it gets a little bit more experimentation-y. I can go into detail in really any piece of code after I get the kind of bulk of it down. But if you're ever lost, we're going to be in buffer A. And then if you scroll down to grid to particle, particle to grid, or G2P, P2G. Kind of a weird acronym, but is everyone there? Cool. So this function, literally what it does is that step where you gather the stuff to the point and then distribute the point back to the cell or the stuff, the blurry image. So we can start by checking if the mass is equal to 0, just so we don't like divide by 0. Oh yeah, I'm so sorry. That is a bit too large. Maybe I can also do this as well. Can everyone see that? Okay, great. Yeah, there's also a guide up here. That's what we're going to be using. There we go. Also, if you don't know what this coding language is, it's GLSL, and it's basically like C, but in my opinion, better in a lot of ways, because it actually has you can use vectors, which is really confusing in C. So this the first thing we want to do after that is create a vector. And this vector has the velocity as well as the mass stored in it. And the way that we fetch the velocity and the mass, like I said before, was using like texture fetch. I think in native GLSL, you would use something like texture, but because I'm compressing the particles in like this really weird backwards way, I created my own function so that's called texture fetch bilinear, I believe. I'll just copy that. And the first parameter here is the buffer right here. In what the buffer is literally just a texture. So like I could grab like any kind of texture here, like I don't know, this rock map, and that's basically what this is, but we can store to it. Oh, also, since you're just coming in, if you go onto Discord, there's a link to this shader toy.
I saw it.
Oh, okay, cool. Cool. Yep. So the second parameter here is actually our position. Because we have to linearly interpolate the texture to make it based on the weights, we have to feed it the position. So I just have my particle P, and it's a struct. So it has a position that is already stored in it, luckily for us. This is probably, I hope, the most intuitive part. We literally just take position and we take our velocity. To get only the velocity, I guess you call that a swizzle by taking the dot xy. So that's the velocity, and then we just multiply it by delta time, which I already have set up in the code. Any questions there? I hope that's mostly self-explanatory. Cool. So the next part is the pressure right here. There's a bunch of different equations, but I think the most accurate one that I've seen is like you actually use like to the power of 7th or something when you multiply the density for water. But to the power of 7, it gets very explosiony very quickly. So we're actually just going to use something linear. So we'll just take the mass, which is the z component here, and we'll just multiply it by like some value, like 0.1. Or maybe something a little bit higher than that, yeah. I'll go into what those other terms are later. So nothing super scientific here, just whatever feels right to convert density to pressure. Let's see. Okay. So now this is the point where we need to calculate the weight. And so this is the part where if you have a particle, you need to distribute it back to the grid, to that center cell piece. And we need two things. We need the position relative to this centerpiece, as well as the actual information of the particle. So in one of the papers, I don't know, they just use deep position, just because I don't know why. Maybe delta position, that's what they meant, but I just went with the same naming convention. And then we just offset it, our particle that we're in right now, to just get it back into the center. So this position is the position of the center cell, and the p dot position is the position of the particle, because it's particle dot position. Cool. So now we have the distance between those 2 points. Or not the distance, but the vector, that's a better word, of those 2 points. This will be our blur kernel or blur function. So before, we were using a linear interpolation kernel, which, if you were to look at it, literally just looks something like this. And it's nothing super fancy. I mean, linear interpolation. you would imagine. So the closer you are to this, the closer you are to like 1.0. And the farther away, you're getting really close to like 0.0. But the kernels are the most important thing in particle simulation. And it might be a bit confusing why, because it was confusing for me why you couldn't just throw like a linear interpolated kernel at everything. And it's still kind of weird, and I don't think a lot of people know this, but you can mix kernels. You don't have to distribute the particle with one kernel and then use the same one again. You can mix different ones. So this one's super cheap. So that's why I used it here, because it's actually surprisingly not that important. But the second kernel, the one to distribute, looks like, I believe, like this. So it's a lot more expensive to compute. Any questions there? I know the visualization is not the best, but good. Okay. Yeah. So that's one way that you could, if you're ever looking for a performance gain in a particle simulation, if you gather with the linear kernel, it will be like I don't know, probably like 2 times faster, because it's just so much more cheaper. But you will get some loss in quality. Just mind that. So I have this function that's called G that just does that for us. I think this equation was the one that Michael was also using in his particle simulation, and it works really well. I've tried other kernels, but this one just seems to do its job really well. Yep. So now we just need to apply the kernel to the center cell that we have right up there. So the center cell in this example is just called C dot mass. We can grab that plus and equals the weight of what we just calculated times the floating point value, because I believe mass is an integer here. So yep, now with just that one statement, we have distributed every particle in this whole thing to the grid. Now we just need to do the same thing to the velocity. So we'll call float p dot mass times velocity mass dot xy. And if you're wondering, wait, why are we multiplying the mass by the velocity? Well, that's because you don't want every single particle when grouped into the center to have the exact same weighting. You want every single particle to be weighted on how important it is to the simulation. And if something has like 10 density right here and 1 density over here, this one is probably a lot more important. So that's why we multiply it by the mass here. And then later on, we just normalize it back by dividing the total density by the current mass velocity. Does that make sense? I know that's a lot of words. Okay. If anything's confusing, don't worry, because this took me not gonna lie, like 5 years to get to the point that I am. Yeah.
So the elements mixture, is this the grid of products or velocity kind of thing?
Line 71. Or which line?
I mean, like, where you define no mass as this texture effect, like what, sort of like, what is it supposed to represent?
Oh, yes. Like this texture fetch right up here. So yeah, this is the point. This is the linear kernel right here. This is when you grab all of the data from the grid and then push it to each particle. Just to get like the general overview again, like with all this terminology, if you're gonna leave here today with how particle simulations work, it goes, you have a bunch of particles and you basically splat them onto some kind of 2D canvas. And this canvas is blurry because the resolution is so low. So because it's blurry, you get a lot of stability. And then you feed all of the information from this blurry canvas back onto the particles again. And that is like the essence of what this simulation method is. The reason why we do that is a bit more complicated, but it just ended up working the way that it did to be this good.
So that, I mean, in terms of what it's supposed to represent, what is no mass? Like, what is it?
Oh yeah, sorry. I just for simplicity, I just took the velocity. Oh, that was wrong, but oh well. See, I just took the velocity and then like tacked on mass.
Like,
So
plus?
so the dot xy member is the velocity, and then the dot z member is the mass. I know I could have written that better, but I couldn't think of a better way to format that because the texture needed to be in the same function. But if you wanted something that was a little bit more clear, maybe I could write it like this. Oh, okay. Yeah, sometimes OpenGL is a little bit weird, and you had to add vectors that shouldn't be together just to make it faster and yeah. Cool. So now once we have this right, now only the velocities here are conserved. There's no pressure solving because it just, you gather all the velocity together and whatever that is, it just sends it off. So I'll show you that in a minute, but let's finish by just using my clusterize. I believe that's how I spelled it. There. Oh yeah, there we go. Which just takes in the current cell, the current particle, as well as the current position of the cell. I mean, I hope I know this function probably could be elaborated on, but I hope that makes sense why those are the input parameters. Yeah, you just need them to put all the particles into one cell. Hopefully if we compile this, it will run. Oh, there we go. Yeah. So I have gravity on. Yeah, if the gravity was off, there literally would be no pressure or anything going. Maybe I can show you what that looks like. So like, because there's no velocity anywhere, nothing's going anywhere because there's no pressure. So let's fix that. If we look at this function, the way that we solve pressure is through velocity. Because you need to push something out of the way to make sure that the density is consistent. This is where it gets a little linear algebra, and it's kind of hard for even me to understand. But I understand what this function does, although I wish I understood it better. But this basically means for any vector on here, depending on where your position is, it will always point away when it's adding. And then it just also adds the pressure onto that magnitude. Or something along those lines. Don't forget an addition sign there. And if we compile it, yay, we get pressure. So you get some gas. And I don't know, I guess once you're at this point, this is probably when things get a lot more fun, because oftentimes you can spend like hours and hours debugging this when you're writing it from scratch. So congratulations. And yeah, you can see the pressure works and everything. Any questions there? No? Okay, cool.
With 3D, we just increase like the pressure to be 3D and then have like velocity match.
Yeah. Do you want me to show you the 3D version? Because I have it.
Oh, sure, if you want.
Sure, I can just show you that really quick. Well, this is a tiny bit different, but like it's basically the same thing. I just get rid of like that because that doesn't matter. So yeah, it's like the exact same thing. Sorry, that's clutter. With some janky code. Sorry, that was an experimentation. But yeah, then you get this. If you're maybe I need to refresh the page on that one. Oh, I understand. Needs to be full screen. So yeah, this is what it would look like in 3D. Yeah. So now, how do we get this to look more like water and less like a gas? So the whole idea here is rest density. The whole application here literally just wants to push everything away from itself. So you get no surface tension. And surface tension is a bit difficult to solve in a lot of simulations, but here it's actually super fast and interesting. Since we have the gradient of the density, if we just push, right, if it wants to go like this, but the density is like, I don't know, like 1.0, and that's perfect, and this is the pressure, well, then we could just get rid of that and subtract it by some value. Now, if it was like 1.2, it might just be a little bit tiny. So the way that we do that is literally by just subtracting the velocity, or the density, like this. Oh, that's kind of weird. So we could just set the rest density to 0.0 here. Does that make sense of why that sets the rest density that way? Cool. So then once we just literally do that, then we have water, but with zero gravity, because I forgot to turn gravity back on. So if you ever wondered what space water looked like, there we go. It's a bit too much there. Perfect. Yeah, I mean, the technique's not perfect. It doesn't look like something out of a, Frozen 2. Hashtag best fluid simulation film. In my opinion, yeah. Avatar 2 is really good too. Not gonna lie. Yeah. Yeah, there's some artifacts where things clump together because the precision is kind of bad. But yeah, you can just start experimenting with it here. So if you're like, well, I kind of wish that the rest density was a little bit higher, you could just increase that. And then you might get something a little bit more water-like. But here's the issue with any simulation. You get this, which is explosions. This happens because the pressure is usually set too high, or there's numerical instability, and it is super, super annoying. With my monitor, I think I'm getting like 100 and something FPS, and sometimes it can struggle to simulate anything that looks remotely fluid-like because it's just so slow. Because I need to set the delta time super, super low. But I think I set it at 0.3 here. And I think this looks the best in my opinion, but you guys can play around with those numbers. Yeah. What time is it? Okay. That is the main bulk of like everything you need to know to get started with particle clustering. Does anybody have like any open-ended questions or like anything that was kind of bothering them?
So you have to like smooth out. So for example, like right now we can see individual particles.
Yeah.
So you know if there's a way to like, I guess for like the 3D case, if you didn't want to see like individual particles, how would you
Yeah.
make that look more like fluid like that?
So I think in this case I have a blur parameter, but if you make it too blurry, it looks blurry. I forgot where. I think it's this here, but that does, yeah. Oh, maybe it needs to go higher. Oh yeah, here you go. Maybe it's a little bit more blurry, but I don't know. I like it a little bit more particly.
Okay.
But for like you were saying for 3D though, for 3D it gets a bit difficult because now there's a lot of different mesh methods. One involves generating a mesh. So if you have all these particles, you can try to mesh the surface. I haven't done it before, but if you're aiming for a real-time application, I'd recommend what I've seen somebody do in the past is instead of having just a point on the screen, what they do is they make a flat plane and they make it like transparent or something. And because it's a flat plane, if you have like a wave or something, you'll get a pretty good approximation of that wave because they're just all tiny flat planes. So the surface will look fairly continuous, but you'll get something super, super fast. There's also other technology that is slow, and I don't like slow things. So, yep. Yeah. Any other questions? No? Okay. Oh, yeah. So, you can use a sign distance field, but the way that I've seen people do it, there's like a wide variety. But I think the most popular I've seen is something remotely close to like marching. Have you ever heard of marching cubes?
Yeah.
I think it's like marching cubes, but it's almost like weighted marching cubes. And it operates not on the particles themselves, but the 3D grid. Because there's like a density parameter, you can technically just think about it as like you were saying, kind of like a sign distance field. And then you construct the mesh from that. I know I've heard of like zebra fluid or something like that. They were actually using AI to construct their mesh. I heard loosely. I don't remember if that's correct or not. There's like a million and one different methods to do that, yeah. But really fascinating. Yep. If you guys want, since I have a little bit extra time, I can show you really briefly a second method that works a lot more easy to understand, but it's a lot more limited. Really quick, just for fun. I think this one was the best one that was working pretty well. So this one works per cell, which is weird because there's actually no points. And because there's so many pixels on the screen, it works pretty well. But for something like 3D, it does not work really well because you need a lot of cubes to do this properly. Yeah, to get this resolution in 3D, it's the resolution cubed. So I think there's maybe like 2 million particles on my screen right now, or maybe even 4 million, somewhere around there. Wait, yeah, 2 or 4 million. But then for 3D of this quality, you would need like 1,000 times that, I think, which is in ludicrous. That's like 1 billion cells. But yeah, this is a different technique that I was working on before. The surface tension may be a little bit better, but yeah. Oh, also, maybe this would help a little bit, but I made the resolution scale super low just so you could see the tiny particles. So this one has even more particles. Yeah, so it runs really smoothly and fast. But like once you start getting super big, you can't really see any of the waves anymore because they're so small. So that's something I kind of like about this technique. It's kind of fun to do. So yeah, and then you can do weird stuff like, I think, like this with fluid simulation on Shader Toy. I don't know, just kind of be creative. I love the Pervoxel effect in things, so I was trying to go for that here. They're all tiny little cubes. So yep. Thanks guys for coming. It's been a lot of fun. And I hope you learned something. That's it for me. Cool.
Thank you.
Yeah, thanks guys. What? Yeah. I actually, how do I, there we go.